Hello everyone, welcome to lecture 4. So, plan for this lecture is as follows. We will discuss perfect secrecy, which is the first formal notion of security and which is also the strongest notion of secrecy, and we will also discuss various equivalent definitions of perfect secrecy. So, the definition of perfect security was given by Claude Shannon in his classical work in 1948, and Shannon is often considered as the father of information theory. And this notion of security is also called as unconditional security and information theoretic security. So, the attack model that is considered in the definition of perfect security is the cipher text only attack model, where we assume that we have a sender and a receiver who have agreed upon a random key value k, and we assume that sender has encrypted a single message m using a publicly known encryption process under that key k, and the cipher text has been intercepted by the adversary. The interesting part of this attack model is that we assume here that the adversary is computationally unbounded. That means, we make no assumption whatsoever about his computing power. We assume that he can do any kind of computation, be it brute force or any other computation. So, that is the interesting aspect of this security model. Informally, perfect security says that irrespective of any prior information that the attacker has about the underlying plain text, seeing the cipher text provides no additional information to him about the underlying plain text. That means, seeing the cipher text is absolutely useless for the attacker. Whatever it could infer about the message from the cipher text, same it could have already inferred before any cipher text would have been communicated. So, here we have two entities. We have the prior information and we have the term no additional information. So, we have to now learn little bit of maths to understand how to formalize these two notions, namely that of prior information and that of no additional information, right. So, imagine we are given a publicly known cipher, namely a triplet of algorithms, key generation algorithm, encryption algorithm and a decryption algorithm. Then any attacker has the following information about the encryption process, right. Namely, he knows three key spaces, it knows three spaces, namely the message space, the key space and the ciphertext space, where the message space is the set of all legitimate messages which could be encrypted by the encryption process. Key space denotes all possible keys which could be output by the key generation algorithm, and the ciphertext denotes all possible ciphertext which could be generated by the decryption algorithm, which could be generated by the encryption algorithm, right. So, now from the viewpoint of the attacker, any encryption scheme induces three probability distribution, one probability distribution over the message space, one probability distribution over the key space and one probability distribution over the ciphertext space. So, now let us go over these probability distributions one by one. The first probability distribution is over the key space, and this is induced by the key generation algorithm. So, remember, as per the Kirchhoff's principle, we assume that the steps of the key generation algorithm, encryption algorithm and decryption algorithm are publicly known to the attacker. And we also discussed that key generation algorithm has to be a randomized algorithm. That means, every time we run the key generation algorithm, it is going to output a possible candidate key from the key space with certain probability. So, that is what we mean by the probability distribution over the key space induced by the key generation algorithm. Also, we discussed in one of the earlier lectures that in most of the cases, the key generation algorithm is going to output a uniformly random key from the key space. Namely, if the key space size is this cardinality of key space, then any candidate key could be generated with probability 1 over the key space. So, that is the uniform distribution over the key space which adversary would already have if it knows the steps of key generation algorithm. But it is not necessary that your key generation algorithm always outputs uniformly random keys from the key space. So, that would be inducing another kind of probability distribution. Whatever is the case, since the steps of the key generation algorithms are publicly known, we know that from the viewpoint of the attacker, there is a probability distribution over different values of keys which could occur with different probabilities, and to capture that we introduce this notation boldface k, which is a random variable and which denotes the value of candidate key which could be obtained by running the key generation algorithm. And since the key generation algorithm is going to be a randomized algorithm, it is not the case that every time we run the key generation algorithm we obtain the same value of little k, and different values of little k could occur with different probabilities. To denote what value of little k has been obtained by running the key generation algorithm, we introduced this random variable boldface k. So, the notation probability random variable k is equal to little k denotes the probability with which the key generation algorithm would output the candidate value of key to be little k. That is the probability distribution that adversary has about the key space. The next important probability distribution is that over the plain text space, and this models any kind of prior information that the attacker might have about the underlying plain text. For example, if the attacker already knows or feels that depending upon the underlying context, sender would either encrypt the message attack 70% times or the message retreat 30% time, then that is a probability distribution over the message space that is induced and known to the attacker. But it might be the case that attacker is completely clueless what exactly is going to be the message. It could be any uniformly random message from the plain text space. In that case, the probability distribution is a uniform probability distribution. So, we introduce this random variable boldface m, which is a random variable to denote the candidate plain text which sender might encrypt using the encryption algorithm, and since attacker does not exactly know what exactly is the message going to be encrypted, we have probability for different candidate messages to occur with different probabilities. So, the notation probability random variable m equal to little m denotes the probability with which attacker feels that sender would encrypt the plain text m using the encryption algorithm. So, that is the probability distribution over the plain text space. And the third probability distribution is the probability distribution over the ciphertext space, and this is determined by the probability distribution over the message space and the key space and the steps of the encryption process. Because once attacker knows what is the probability that a certain plain text would be encrypted by the sender and what is the probability that a candidate key would be obtained by the key generation algorithm, then by running the steps of the encryption algorithm over that candidate plain text and the candidate key, adversary can find out what is the probability of occurrence of a certain ciphertext. So, we introduce this third random variable boldface c to denote the value of the candidate ciphertext, and the notation probability the random variable c equal to little c denotes the probability with which the encryption algorithm would output the ciphertext c. Right. So, notice that the random variables m and k are independent of each other because the key is obtained by running the key generation algorithm, which is run independent of what message is going to be encrypted by the ENC algorithm, whereas the random variable c, it depends upon the random value of the random variable m and the random variable k. So, now let us see a numerical example to understand these concepts in a better fashion. So, imagine I have a candidate encryption process where the candidate messages could be either the character A or B or C or D. In the same way, imagine I have a key generation algorithm which could output 3 keys with different probabilities, and say the attacker has the following probability distribution over the plain text space. That means, it knows depending upon the underlying context, it feels or it knows somehow that the message could be either A with probability 1 by 4 or the message could be B with probability 3 by 10 and so on. In the same way, assume that the key generation algorithm outputs the candidate key to be K1, K2, K3 with probability 1 by 4, 1 by 2 and 1 by 4 respectively. So, that is a probability distribution over the key space that attacker has. And imagine the adversary knows the steps of the encryption algorithm. So, it could compute an encryption matrix where along the columns you have the candidate plain text, namely A, B, C, D, right. So, these are the candidate plain text, and here you have the candidate keys which could be obtained by running the key generation algorithm. So, this value 3 denotes that the encryption algorithm is going to output ciphertext 3 if the plain text would have been A and the key would have been K1. In the same way, for example, this last entry denotes that the ciphertext will be 2 if the plain text would have been D and the key would have been K3 and so on. And adversary could compute this matrix because it knows the steps of the algorithm and it knows the different candidate values of plain text and the candidate values of key, right. So, that is the information that is available with the attacker. So, now let us try to compute the probability distribution over the ciphertext space, right. So, as you can see from the encryption matrix, the ciphertext could be either 1 or 2 or 3 or 4. So, let us try to compute the probability with which the ciphertext could be 1 or 2 or 3 or 4. So, let us first compute the probability that what is the probability that encryption algorithm produces ciphertext to be 1. So, now if you see the encryption matrix, the ciphertext could be 1 if the plain text is B and the key is K2, that is one option or one condition under which the ciphertext will be 1. The other condition in which the ciphertext could be 1 is when the plain text is C and the key would have been K3, and the third condition under which the ciphertext could be 1 is when the plain text is D and the key would have been K1, and all these three conditions or events are independent of each other. So, we apply the sum rule here. So, the first term here denotes the probability that the key would have been K2, that means by running the key generation algorithm, sender would have obtained the key to be K2, and the probability that sender would have used the message B for encryption. If both these events occur together, then the ciphertext would have been 1. The second term denotes the other possible condition in which the ciphertext could have been 1, namely the plain text that sender wants to encrypt is C and the key that is obtained by running the key generation algorithm is K3. And the third term here denotes the probability of occurrence of the third condition, namely the plain text is D and the key generation algorithm outputs the key to be K1. And since we know the value of each of these individual probabilities which is available to the attacker can compute this, and hence it knows that the probability that encryption algorithm could produce ciphertext to be 1 is 0.2625. So, that is the value of probability of occurrence of 1 as the ciphertext. In the same way, let us try to compute what is the probability that the ciphertext could be 2, right. Again, if you see the encryption matrix, there are three possible conditions in which the ciphertext could be 2. So, the first condition is if sender would have encrypted the plain text C and the key that is used by the sender, namely the key generation algorithm, outputs the key to be K1. So, that is this underlying term. The second condition in which the ciphertext character would have been 2 is if the plain text would have been D and the key generation algorithm for sender would have output the key to be K2. So, that is this second term. And the third condition under which the ciphertext character could have been 2 is if the plain text would have been D and the key would have been K3. Again, we know all these individual probabilities and we can sum them together to obtain the probability of ciphertext being 2 being produced by the encryption algorithm. In the same way, you can compute the remaining probabilities, namely the probability of ciphertext being 3 and the probability that ciphertext character is 4. And that gives you the probability distribution over the ciphertext space. Not only we can compute the probability distribution over the ciphertext space, we can also compute some additional values, namely some kind of some conditional probabilities. For example, let us try to compute the conditional probability that given the plain text is M, what is the probability that ciphertext would have been C, right. So, for instance, suppose let us try to compute the value of probability that ciphertext is 1 given that plain text is equal to A. So, again if we see the encryption matrix, if you see the column under the plain text A, then you can see that if the plain text would have been A, no way it is possible that the ciphertext could be 1, because the encryption of A could give either the ciphertext being 3 or ciphertext being 3 or ciphertext being 4. For no value of K, no value of key, the encryption of A would have given you the ciphertext to be 1. That is why we can say that the probability, the conditional probability that ciphertext is 1 given the plain text is A is 0, right. In the same way, the conditional probability that ciphertext is going to be 2 given the plain text is 1 is again 0, because again you can see the encryption matrix or the encryption algorithm which states that for no value of key, the encryption of A under that key would give you the ciphertext value 2. Now, let us compute the conditional probability that given the message A, what is the probability ciphertext is equal to 3. Now, if you see the encryption matrix under the plain text A, there are two values of keys, namely K1 and K2, both of which could produce an encryption of A to be 3. And since the key generation algorithm is a randomized algorithm, the probability that the key is equal to K1 is given to you, the probability that key is equal to K2 is given to you, and if any of these two events occur, then the encryption of A under the key K1 or under the key K2 would have given you the ciphertext equal to 3. So, the conditional probability that given the plain text is A, you obtain the ciphertext 3 is 0.75, and in the same way, if you want to compute the conditional probability that given the plain text is A, what is the probability ciphertext equal to 4, then again if you look into the encryption matrix, you can see that if the plain text is A, then the only condition in which you can obtain the ciphertext to be 4 is if the key generation algorithm would have produced the key to be K3, and the probability that the key generation algorithm would produce the key to be K3 is 0.25, right. In the same way, you could compute other conditional probabilities as well. So, now let us see the original definition of perfect security as given by Shannon. So, informal requirement, recall the informal requirement from the perfect secrecy is that we will say an encryption process to be perfectly secure if irrespective of any prior information the attacker has about the underlying plain text, the ciphertext that it intercepts leak no additional information about the plain text. And now we know how to model this prior information, that is precisely the probability distribution over the plain text space that attacker has. And now we can also mathematically capture what exactly we mean by no additional information. So, formally an encryption process, namely a collection of algorithms, key generation, ink and DEC over a plain text space M is called perfectly secure if for every probability distribution over the plain text space and key space and for every plain text M belonging to the plain text space according to that probability distribution and for every ciphertext C belonging to the ciphertext space, the following equality holds, right. So, let us try to understand what exactly the LHS and the RHS of this equality stands for. So, if you consider the RHS part of this equality, namely the probability that the plain text is equal to small m, little m, that is precisely the a priori probability that message M could be communicated by the sender. That is the prior information about the underlying plain text before any communication has happened from the sender to receiver, before any key generation algorithm has been used and the message has been encrypted. That is the a priori information about the underlying plain text. Whereas the LHS part of this equality, namely the conditional probability that the plain text is equal to M given the ciphertext equal to C, that is a posteriori probability that the message M is encrypted in C. That means, given that adversary has seen or intercepted the ciphertext C, what is the probability that the plain text M, little m is encrypted in this ciphertext C. So, intuitively when we say that these two probabilities are equal, it means that whatever the adversary knew about the underlying plain text before any ciphertext was communicated, with same probability adversary knows that the plain text could be M and in the given ciphertext C. That means, observing the ciphertext C does not change attacker's knowledge about the distribution of the plain text. Whatever the attacker's knowledge was before seeing the ciphertext, the same knowledge it has even after seeing the ciphertext. And moreover, it holds even if adversary is computationally unbounded. That is the importance of this definition. This definition does not put any kind of restriction on the computational power of the adversary. Even if adversary knows the steps of the algorithm, even if it knows what could be the candidate keys, even if it is allowed to do brute force, its view or its knowledge about the underlying plain text or the distribution of the plain text should not change before and after seeing the ciphertext. If that holds, then we say that our underlying encryption process is perfectly secure. Notice that in this definition I have highlighted few things, namely I have said that the condition should hold for every probability distribution over the plain text space. That means, it does not matter whether the distribution over the plain text space is a uniform distribution or a biased distribution, the condition should hold for any possible probability distribution over the message space. In the same way, the condition or the equality should hold for any kind of probability distribution over the key space, whether it is a uniformly generated key, whether the key generation algorithm outputs uniformly generated random keys or biased keys, still the condition should hold. Moreover, once we fix the probability distribution over the plain text space and the key space, the condition should hold for every plain text belonging to the message space and every candidate ciphertext belonging to the ciphertext space, right. So, now what we will do is we will see some alternate equivalent definitions for perfect security. So, this is the original definition of perfect security as given by Shannon, and the interpretation of the equality of these two probabilities is that the probability of knowing a plain text remains the same before and after seeing the ciphertext. That is the interpretation of the original definition of perfect security as given by Shannon. Now, let us see the first alternate definition. The first alternate definition says that we will say an encryption process, encryption scheme to be perfectly secure if for every probability distribution over the plain text space and key space and for every pair of message M0, M1 which occurs with non-zero probability with respect to that probability distribution and every ciphertext C, the following equality should hold. The equality says that the conditional probability that ciphertext is C given the plain text is M0 is same as the conditional probability that ciphertext is C given the plain text is M1. The interpretation of this equality is that the probability distribution of the ciphertext is independent of what exactly is your underlying plain text. That means, if the adversary sees the ciphertext C over the channel, then it does not matter whether the plain text is M0 or whether the plain text is M1, with equal probability for the from the viewpoint of the attacker, the ciphertext C should be an candidate encryption of M0 as well as a candidate encryption of M1. There should not be any bias in the probability, whether it is an encryption of M0 or whether it is an encryption of M1. That means, the ciphertext distribution should be independent of the underlying plain text. So, now what we are going to do next is we are going to prove that both these two definitions are equivalent. Namely, we will show that if there is an encryption process which satisfies the original condition of Shannon's perfect security, then the same encryption process has to satisfy the alternate definition and vice versa. So, let us first prove the equivalence of the definition, assuming that we have an encryption process which satisfies the condition of the alternate definition. Namely, we assume that we have an encryption process where for every probability distribution, the conditional probability that M0 is encrypted in C and M1 is encrypted in C is same, and we call that probability to be, say, delta for all pair of messages M0, M1 in the plain text space and for all ciphertext C belonging to the ciphertext space. Given this, we will prove that the original condition of the Shannon's perfect security is also true for the encryption process. Namely, the conditional probability that the message is M in the ciphertext C is same as the probability that plain text is M, right. So, what we are going to do is assume we have an arbitrary plain text and arbitrary ciphertext character. Now, let us try to compute the conditional probability that message is M given the ciphertext is C. So, what I am going to do here is I am going to apply the Bayes theorem here, and by applying the Bayes theorem I can change the numerator and denominator of the conditional probabilities. So, in the left hand side the numerator is message being M and the denominator is ciphertext being C. So, I am applying the Bayes theorem and rewriting the same expression in LHS where I am changing the numerator and denominator, and as per the Bayes theorem I will get the right hand side part, right. So, now let us try to compute the value of probability what is C equal to little c. Now, the probability that your ciphertext is little c is going to be this summation. This summation state that you take all possible messages from the plain text space and find out what is the probability that the message is that candidate plain text, namely M dash, and given that the message is M dash, what is the probability that M dash is encrypted in C. That will give you the probability distribution over the ciphertext being little c, right, because you have all what you have to basically do is imagine you have the plain text space, you take each of the plain text candidate plain text, that is precisely the first term in this summation, and once you have fixed that candidate plain text, you just compute what is the probability that that candidate plain text will take you to the ciphertext little c. that is his second term. And if you multiply all this, if these two probabilities and take the summation over all candidate plain text, that will give you the probability distribution of ciphertext being little c. Now, as per our hypothesis of the condition, we know that the conditional probability that ciphertext is little c given the plain text is m dash is same for all m dash, namely it is delta, because that is what is the assumption that we are making. We are making the assumption that our encryption process satisfies the alternate condition. So, for every m dash I can replace the second term in the summation by delta, and as a result I get this simplified form of the summation, and I can now take out delta common, and what I will be left with summation of probabilities over the plain text space, that the plain text is little m dash. And if as per the rules of probability, if I sum up all those probabilities I will get 1. So, that means I can say that the probability that ciphertext is little c is nothing but delta. Okay. So, we have computed the value of probability of c equal to little c, that is delta. Now, let us try to compute the probability, conditional probability that ciphertext is little c given the plain text is m, that is the numerator part of this RHS expression. And again, as per our hypothesis of this theorem or this lemma, we already know that the given the plain text is little m, the probability that ciphertext will be c is nothing but delta, and that is irrespective of what is my little m. It could be m0, it could be m1, it could be m2. For any candidate m from the plain text space, the probability that it could lead to the ciphertext being little c is delta. So, that means the numerator part of this RHS expression is also delta. Hence, I can say that my original LHS part, namely the conditional probability that ciphertext, a plain text is m, little m given the ciphertext is little c, is nothing but this equality, and in the numerator as well as in denominator I have the delta. So, I can cancel it out, and hence I obtain this conditional probability is nothing but the probability that plain text is little m, which is precisely what exactly we wanted to prove. That means, we have proved that if the encryption process satisfies the condition of the alternate definition, then it also has to satisfy the condition of original Shannon's definition, right. So, now let us do the proof in the reverse direction. Namely, we assume that we have an encryption process which satisfies the condition of the original Shannon's definition, that is the conditional probability that message is little m given the ciphertext is little c is same as the probability that message is little m for all messages in the plain text space and all ciphertext in the ciphertext space. Given this, we will prove that the distribution of the ciphertext is independent of the underlying plain text. Namely, it does not matter whether the plain text is m0 or whether the plain text is m1, with equal probability it could lead to the ciphertext little c, and this holds for every pair of messages m0 comma m1 from the plain text space and every ciphertext c from the ciphertext space, right. So, let us first try to compute the probability that ciphertext is little c given the plain text is m0. For this, we are going to use the fact that as per the given condition, since the encryption scheme satisfies the original Shannon condition, we know that the conditional probability that message is m0 given the ciphertext is c is same as the probability that message is m0, right. So, now what I am going to do is I am going to expand my LHS part here using the Bayes theorem, where I have to where I am just changing the numerator and the denominator of the conditional probability, and by applying the Bayes theorem I get this equality. Now, what I can do is I can cancel out this common term from both the LHS and the RHS, and hence I obtain that the conditional probability that little m0 will lead to an encryption of c is same as the probability that ciphertext is little c. By applying the same logic, I can conclude that the conditional probability that ciphertext is little c given the plain text is m1 is same as the probability that ciphertext is little c. As a result, both this conditional probability that m0 will lead to an encryption of c and the probability that m1 will lead to an encryption of c are same, namely it is probability that ciphertext is equal to little c. That means, we have proved that if the original Shannon's condition is satisfied, then the encryption process also has to satisfy the condition for the alternate definition. That means both these definitions are equivalent to each other. So, if you are given an encryption process and if you are asked to prove whether it is perfectly secure or not, then you can either prove it as per the original Shannon's condition or you can prove it as per the first alternate definition. Now, let us see another equivalent definition of perfect security, and before going into this definition, let us first try to understand the underlying intuition that we want to capture through this definition. So, the goal of the perfect security is the following. Imagine a scenario where a key for the encryption process has been agreed upon between the sender and the receiver, and suppose adversary knows that the candidate plain text for the sender is going to be either M0 or M1, and that too with equal probability. And suppose indeed sender is going to encrypt message M0 or M1 with equal probability, and it encrypts one of these messages randomly using the key K as per the encryption process, computes the ciphertext C and sends it over the channel, and say the attacker intercepts the ciphertext C and the attacker has unbounded computing power. Intuitively, perfect secrecy demands that the adversary's knowledge about the underlying plain text should remain the same even after saying the ciphertext C. So, what was this information about the plain text before any ciphertext was communicated? In this particular case, with probability half from the viewpoint of the attacker, the plain text could be M0, and with probability half the plain text could be M1. Now, perfect secrecy demands that even after seeing the ciphertext C and even after knowing the steps of the encryption process, and even if the adversary has unbounded computing power, the advantage that adversary gets after seeing the ciphertext and learning the underlying plain text should be 0. That means, even after seeing the ciphertext C, the probability that the underlying plain text could be M0 or M1 should be half. That means, adversary can do nothing better than guessing the underlying plain text. That is the basic underlying intuition that we are now going to formalize. And this intuition is formalized by a challenge response game which we call as experiment, and we are going to see that in the rest of this course every security definition is going to be formalized by this kind of challenge response experiment or a game which models something which we want which can happen in reality, right. So, the experiment is as follows. So, we assume that we are given a publicly known cipher, namely a triplet of algorithms and a message space, and the game is played between two entities. The first entity here is an adversary or an algorithm for the attacker, which we denote by this algorithm A, and the algorithm or the adversary is computationally unbounded, and this models the fact that we are trying to capture the notion of perfect secrecy where the adversary is computationally unbounded. And the second entity here is the hypothetical verifier, which is going to model the sender, right. Now, the nomenclature that we are going to follow while naming these kind of experiments is as follows. So, this particular experiment is denoted by this name, and now let us try to decode each of the individual parts of this complicated name. So, the name prefix priv k denotes here that we are trying to model an experiment for a symmetric key encryption process or a private key encryption process. That is why the name priv k. Later on, when we will try to model the security requirement for public key primitives, this priv k will be replaced by pub k. The name or the string EAB denotes here we are considering an adversary where the adversary is only allowed to eavesdrop or just listen the ciphertext, because we are in the ciphertext only attack model. The name A here denotes the name of the algorithm here, and pi denotes the name of the encryption process with respect to which this game is going to be played. So, that is the nomenclature we are going to follow to denote this particular experiment, right. So, now what are the rules of this game? This experiment is going to be a randomized experiment. So, the first step here is that adversary selects a pair of messages from the plain text space, say M0 and M1, with the restriction that their size has to be same. An adversary can choose any pair of message. There is absolutely no restriction which we put that on the pair of message that it can submit to the verifier. The only restriction is that their length has to be same. So, adversary can deterministically pick a pair of message, it could randomly pick a pair of message, it can use any strategy to pick the pair of message that it want to send to the verifier. Now, once the pair of messages are communicated to the verifier, what the verifier is going to do is the following. It is going to run the key generation algorithm, which will output a uniformly random key or a key as per the steps of the key generation algorithm for the verifier, and the verifier is going to randomly pick one of these two messages for encryption. So, the index of the message which is going to pick for encryption is denoted by B, which is picked uniformly randomly. That means, with probability half it might be picking the message M0 for encryption, or with probability half it might be picking the message M1 for encryption. Once it has decided the index of the message, it encrypts that message MB using the key K, which is known only to the verifier, and the ciphertext is given to the adversary. And now the goal of the adversary is to find out the index of the message which has been encrypted in C. That means, the adversary has to find out whether the C that it is seeing is an encryption of M0 or whether it is an encryption of M1. So, after analyzing the ciphertext C as per whatever strategy adversary wants to follow, it gives a prediction, namely it outputs a bit which is either 0 or 1 corresponding to the index which it feels that particular message has been encrypted in the ciphertext C. That means, B dash denotes the index which according to the adversary is the index of the message which is encrypted in the ciphertext C. That is the experiment, and as you can see, this is a randomized experiment because the adversary could pick any pair of message as per its randomness. In the same way, the verifier is going to pick any random message out of this pair for encryption, and the key could be any random key as per the key generation algorithm. Now, the output of the experiment is decided as follows. We say that the output of the experiment is 1, or which is interpreted as adversary has won the game if it has correctly predicted what exactly is the message which is encrypted in the ciphertext C. That means, if it correctly outputs B dash equal to B, then we say that the adversary has won this experiment, or the adversary's experiment's output is 1. On the other hand, if the adversary incorrectly identifies what is encrypted in the ciphertext C, that means it outputs B dash which is different from B, then we say that the output of the experiment is 0, which is interpreted as adversary has lost the game, right. Now, this is the experiment, and now we have a definition which says that an encryption process pi with respect to which this game has been played is perfectly indistinguishable if for every attacker who participates in this game, the probability that the output of the experiment is 1. That means, the probability that the adversary outputs B equal to B dash in the experiment is half. If it is more than half, then we say that the encryption process is not perfectly indistinguishable. Also, the probability here is taken over the randomness over the adversary and over the randomness of the verifier, namely the value of B and the value of K used output by the key generation algorithm, right. So, that is our third equivalent definition of perfect secrecy. So, the original definition of perfect secrecy as given by Shannon was this. We saw the first equivalent definition, and now we have this game based definition, right. So, we have now three different definitions, and it can be proved that all these three definitions are equivalent to each other. We already proved that the first two definitions are equivalent to each other. We can also prove that this third definition is equivalent to the first definition, and the third definition is also equivalent to the second definition. That means, if you are given an encryption process, we can prove it to be secure as per any of these three conditions. We can directly prove it using the Shannon's original definition, we can try to prove it using the equivalent definition, or we can try to prove it using the game based definition, right. So, these are the three equivalent definitions of perfect secrecy. So, now I would like to stress little bit on this game based definition. So, this game based definition describes the notion of what we call as perfect indistinguishability. That means, the ciphertext is completely indistinguishable from the viewpoint of the attacker, and it leaks no information whatsoever whether it is an encryption of M0 or whether it is an encryption of M1. And this notion of indistinguishability is very important, because for the rest of the course we will see that all the definitions that we are going to formulate will be in terms of the notion of indistinguishability, right. So, now let us do an example here, and we will prove that the Vigenere cipher which we have discussed in the last lecture is not perfectly secure. So, we are going to consider an instance of Vigenere's cipher where the message space and the ciphertext space are going to be of length 2. Namely, the message plain text is going to be a 2 character string and the ciphertext is going to be a 2 character string. That is why the message space and the ciphertext space are strings over the set 0 to 25 cross 0 to 25. Now, the key generation algorithm for this instance of Vigenere's cipher is going to do the following. Since the message string plain text string is of length 2, then the key which is going to be used should be of length either 1 or it should be of either length 2. So, that means the period of the key, which is the value t, is a uniformly random value which could be either 1 or 2, and once the period of the key has been selected, we select a key of that much size uniformly randomly from the set 0 to 25. Okay. So, that is a key generation algorithm, and once the key has been picked, we encrypt the plain text that is available with the sender as per the encryption process of the Vigenere cipher. Namely, we divide the plain text into blocks of size t. If t is equal to 1, that means the same key is used to encrypt both the characters of the plain text, whereas if t is equal to 2, then we divide the plain text into one single block of size 2 and encrypt the whole block in one go using the two characters of the key. That is the encryption process, and the decryption process is just the reverse operation of the corresponding encryption process. So, now we are going to prove that this instance of Vigenere's cipher is not perfectly secure. That means, we will give a concrete attack where the attacker can significantly find out what exactly is the underlying message which has been encrypted. And we are going to use the game based definition here, namely we will show an instance of the game here where we will show that the distinguishing advantage of the attacker is significantly better than half. So, the instance of the experiment here is as follows. So, adversary submits the following pair of message. It submits a message M0 which consists of the same characters, say 00, and it submits another plain text M1 which consists of two different plain text characters, right. Now, as per the rules of the game, the verifier is going to randomly encrypt one of these two messages as per the key generation algorithm. So, it decides whether it is going to encrypt the message M0 or whether it is going to encrypt the message M1 with probability half and half. And once it decided what it is going to encrypt, it runs a key generation algorithm which is going to output a period which could be either 1 or 2, and once the period is generated, a key of that much size is uniformly randomly picked and given to the verifier. And now, using that key, the verifier encrypts and sends the ciphertext to the attacker. So, let the ciphertext character be C1 and C2. Since in this case the plain text which is encrypted consists of 2 characters, the ciphertext is also going to contain 2 characters. Now, the goal of the attacker is to find out, after seeing this ciphertext C, whether this ciphertext C corresponds to an encryption of 00 or whether it corresponds to an encryption of 01. And the adversary does that by applying the following strategy. It compares the two ciphertext characters in C, namely C1 and C2, and if it finds that C1 and C2 are same, then it predicts that the message M0 is encrypted in C, whereas if the ciphertext characters C1 and C2 are different, then it predicts that the message M1 is encrypted in ciphertext C. That is the analysis of the attacker, right. So, now let us see what is the distinguishing advantage of the attacker, whether it can significantly distinguish apart whether the C that it is seeing is an encryption of 00 or whether it is an encryption of 01. We claim that the probability that adversary can win this experiment, namely it can correctly identify what has been encrypted in the ciphertext C, is 0.75, which is significantly better than half. Then that means that this instance of Vigenere's cipher is not perfectly secure. So, now let us prove our claim. So, what is the probability that adversary wins the experiment? The probability adversary wins the experiment is the following. We can view this instance of the experiment as two individual experiments. The experiment where the index B is equal to 0, namely the verifier has selected the message M0 for encryption and C is the encryption of M0, and the second experiment here is the version of the experiment where the value of B is equal to 1. That means, the verifier has selected the message M1 for encryption and C is the encryption of M1. So, the probability that the adversary correctly wins the experiment is the probability that with what is the probability that b is equal to 0, and probability of b equal to 0 is half, and given that b is equal to 0, adversary indeed outputs b dash equal to 0. That is one case in which adversary can win the experiment, and the second case is when b is equal to 1, which can occur with probability half, and given that b is equal to 1, what is the probability that adversary correctly output b dash equal to 1. If we sum these two things, then that gives the winning probability of the adversary for this experiment. So, now let us compute each of these two individual probabilities one by one, right. So, let us first compute the probability that adversary's analysis outputs b dash equal to 0, given that indeed b is equal to 0. That means, we now want to analyze what is the probability that if M0 is encrypted in C, adversary's analysis indeed outputs b dash equal to 0, right. So, if you see the adversary's analysis, adversary outputs b dash equal to 0 only if both the ciphertext characters are same, and if indeed 00 is encrypted, then there are two possibilities, right. The key could be either of period 1 or the key could be of period 2. So, if the plain text 00 is encrypted, right, if the plain text 00 is encrypted with a period of size 1, that means the key size is 1 and the same character of the key is used to encrypt 0 as well as the second 0, then of course, both the ciphertext characters are going to be same. Whereas, if the key is of size 2, right, then the probability that both the ciphertext characters are same is the same as probability with which the key of size 2 satisfies the following condition. Namely, the first character of the key is the same as the second character of the key. If that happens, then again the encryption of the message M0 will produce a ciphertext with both the characters being the same. So, these are the two individual events under which an encryption of M00 encryption of the message 00 will lead to a ciphertext where both the ciphertext characters are same. So, now what is the probability that the key generation algorithm of the verifier outputs a key of size 1? Well, it is 1 by 2, and what is the probability that the key generation algorithm for the verifier outputs a random key of size 2 where both the key characters are the same. The probability of that is 1 by 2 into 1 by 26, right. So, if we sum these two probabilities, then we get the probability that adversary's analysis correctly outputs b dash equal to 0, given that verifier has indeed encrypted the message M0, right. So, that is the first probability we have computed. Now, let us try to compute the second probability here, namely what is the probability that adversary outputs b dash equal to 1, given that indeed b equal to 1. That means, we are now trying to analyze that assume the verifier has encrypted the message 0 comma 1, what is the probability that adversary's analysis also outputs b dash equal to 1. And for this, we are actually going to subtract the complementary probability, namely we will compute the probability that adversary incorrectly outputs b dash equal to 0, given that b equal to 1, and we are going to subtract this probability from 1, and that will give us the required probability. So, now let us try to compute the probability that adversary's analysis or adversary's algorithm outputs b dash equal to 0, given that b equal to 1, right. So, the probability of this event is same as a key of size period 2 is selected with the first character being 1 more than the second character, because for example, if the key is k1 comma k2, where k1 and k2 differs by 1 character, or where the differs in the sense that say the first character is say 1 and the second character is 0 of the key, or say the first character of the key is 2 and the second character of the key is 1, and so on. If this kind of relationship holds between the two characters of the key, and if indeed the message 0 comma 1 is encrypted, then after encryption both the ciphertext characters will be same. Only if this event happens, then adversary will incorrectly end up outputting b dash equal to 0, even though b is equal to 1. Now, what is the probability that a key of period 2 is selected with the first character being 1 more than the second character, and the probability of this is 1 by 2 into 1 by 26, right, because with probability 1 by 2 a key of period 2 could be selected, because with probability half the key could be of period 1, with probability half the key could be with period 2. So, the 1 by 2 here denotes the probability that key is of period 2, and given this, what is the probability that the first character of the key is 1 more than the second character of the key? Well, it is same as 1 by 26, right. So, if we multiply these two probabilities, we get this complementary probability, and if we now subtract this complementary probability from 1, we get our required probability. So, now we have both these individual probabilities computed, and if we sum them together and we have outside 1 by 2 as the common thing, we get that the probability with which adversary analysis in this case could correctly identify what is encrypted is 3 by 4, which is significantly more than 1 by 2, and that means this instance of Vigenere cipher is not perfectly secure. So, that brings me to the end of this lecture. To summarize, in this lecture we discussed the notion of perfect secrecy, which is the first formal notion of secrecy and which is also the strongest form of secrecy, because this notion of security is against an adversary which is computationally unbounded. So, if you achieve perfect secrecy, then that is the best possible notion of secrecy that you can think of. We also discussed some alternate definitions of perfect secrecy, namely the distribution of the cipher text should be independent of the underlying plain text, and we also saw the game based definition which models perfect indistinguishability. I hope you enjoyed this lecture. Thank you.